We will continue with Wilda, and he give us some heads up about low-level Go interfacing operation system. Let's go, Wilda.
1, 2, 1, 2. Yes, perfect. Low level. Hey, hello everyone. I'm glad I'm the last one, so you can run away and you're not gonna miss anything. So what I'm going to cover, this might sound ambiguous, right? I'm actually going to cover some of the low-level stuff. We can get really deep if you want. But I also taking this opportunity to actually describe how Go works in the wider ecosystem where most people are using it, and how you can leverage that for some of the cool things. So a little bit of background on me. I'm in the business for a while, and I started using Go when it was not even version 1 yet. That's a nice picture of me. It's not mine. No, I'm not the author, unfortunately. And I am cycling a lot, although today I'm not on a bicycle here. So first, what is operating system? Right? Everybody clear on what is operating system? Few hands, okay. No, all right. So just so everybody's clear on what's the basic terminology. When we're talking operating system, we're talking the stuff which is between applications which most people write and the hardware. Right? Like you take it for granted that if you start typing something on the keyboard, the stuff appears, right? Well, that was not necessarily true 40 years ago, right? And even it's not true today on some of the smaller devices. It's not given, right? Like maybe sometimes you have to write the driver, you write stuff. Operating systems take care of that, right? So most people write applications and users interact with applications, not with the operating system itself. Very few of them do, mostly programmers, right? So very important part of an operating system is something that is called kernel. Every single operating system has it. Some of them have many smaller ones pieced together, but most of the time, we have just one, and that's the thing that actually runs all the time, right? If you don't do anything on the computer, there is a program that runs all the time, and that's called kernel. And it actually manages all the stuff like handling that you start typing. When you want to do a lot of other things, like you want to see what programs are running on the system, you ask the kernel, so on. And basically, without kernel, you can't do much today. Now, how do you interact with it? It's very important, right? Like, most people don't really do it directly because you have libraries, but that's not always the case on all the places and all the implementations you can get. So there's a thing called system call. Every single operating system has it, and it's a mechanism how you say tell the kernel, do something on my behalf, right? This is the definition from Wikipedia, so I can read it off, but it basically says it handles the stuff between the program and the hardware. And it's a way how to call it. And there is a thing called user space and kernel space. User space is the stuff that runs in the kernel. User space is your applications which you are using. And that's why you have the system call itself. Because inside the kernel, you don't ever call a system call. So, have anybody used some? How many? Okay, everybody did. Sorry. If you've done anything, you did. How many do you think is in this program? Just a random guess, right? Like 1, 2, 15, okay. 50, all right. Thousands? Okay. We'll see later. We'll see later, right? But there is an easy way how to figure out like how things work. And this is a very simple, this is a very stupid program, right? So I have it implemented in a, can everybody see it? Right? So, do you want to, if you want to figure out like how this works, have anybody tried actually to dig deep in the Go source code? Hey, one, cool. Second, wicked. So you're not going to see anything special, but for the rest, let's see. Is it still visible or shall I make it larger? Larger. Okay. Better? Cool. So that's the print line. Doesn't do much. It actually is doing one single thing, and that's actually setting an argument here. That's stdout. That's the standard output. Cool. So let's go next level. Let's just slightly, you go just one up. Looks like there's some printer, print ln, and some write. Let's see what that does. Right, I'm gonna, too small, we're not gonna spend time here, so I'm gonna jump more. Come on. Yeah. Oh, so that failed on me. It failed on me. All right, so I'm gonna navigate manually. Sorry. The navigation didn't work the way I wanted. Anyway, there is a package called syscall. Important one, and there are a lot of files in it. These are generated. So I'm going to navigate this way. As you can see, there's plenty. These are all generated, and you don't really have to care much. But I can show you. You can see what's going on, and I'm on AMD, so I'm going to open this one. And here you have all the implementations. Right, search write. I see here that there's a system, there's a function called write. It actually, larger again, sorry. That's when you use ancient editors. Oh, no, this is Emacs, even worse. So you see the function write. Oh, it does some like unsafe pointer. It's totally, you have no idea what's going on, right? Neither do I. Right, but there's the important bit, which is the syscall function. And that one, I'll show you later, because there's no Go source code for this one. Right. But the important thing is, you see there's something called syswrite, and then some unsafe pointer stuff. Right? It basically takes the arguments and puts them in a syscall in some order. We'll get to details a little later. So apparently there is at least one in this. There's more. We'll see how many. So how you actually make one, right? Like this is a simplified picture of a CPU. Right? That's important because there's this ALU, that's where the computation happens. There's some control unit, which actually makes stuff between memory and so on, and the registers. And there are some rules how you engage in this. All right, important are the registers. That's a storage on the chip itself. Like has everybody clear on like how CPU works? Like registers and a few things here and there, just a bit. Cool. That's enough. So that's where you store information, and then you call something which actually triggers the control unit, and that makes the process do something. There's a thing called syscall table. We're talking now system calls in Linux, right? Because that's the system I use, so easier for me to talk about it. So you see there is this part. I have mouse. Can you see my mouse? Yes. AX. So that's one of the registers is called AX. And you write the number of the syscall, and you need to know all of them. And it's like 300 of them, or 350 now. I don't know. They come and go. A few of them are important. There's like read, write, open, close, stuff you would expect when you work with files, for example. And then in the other registers, you put arguments, right? Like some integer in that one, another is a pointer to some memory, and how much, and so on. For example, in the read file, in the read case. It basically means what file descriptor, which piece of memory, and how many characters to read to that buffer. That's it. Very simple, very straightforward, right? So Windows have them too, but it's very complex, and I'll tell you why. I'll show you why in a minute. So now, you know how it looks from the code, but there is important bit, which is actually the implementation of the syscall function. And that's in, no, I mean oh, this is the whole list, sorry. It's in the ASM underscore, yes. So this is actually the syscall function. All right, it's assembly. That's how it works in Go. It's implemented in assembly. But here you see this like AX, and it says the first argument put here, and then this part syscall. That's actually in the assembly. This part of the CPU instruction, right? Like, hey, this is I'm going to call the system. Now the system takes place, does its own thing here, comes back, and this value actually is it okay or not? Like 0 and 1. It's a clever way to complicate it, and then handle the bad case here, handle the good case here, and it calls the function exit syscall, right? So that's how it works in Go. Now, this is all good, but it's fun stuff for me to dig in, but there are use cases why it's good to actually understand what's going on. And that's all programs use it, and if you're doing anything useful, you might have issues, right? Like, program doesn't work the way you expected, it crashes randomly, and you have no idea why. Or your work, it's on a VM somewhere or some container somewhere, and you're trying to figure out like what's going on, why it doesn't work. Very often what you can see is observe all the system calls that your program does. And there's a utility called strace, which is very useful for this, right? Because it gives you all the syscalls the program does. You need to have permissions for that, right? Like root. But so I'm going to give you a few examples how it works and what it can show you. So this is the simple program before. It doesn't. Now we'll see how many of them are there. So there is a called -c argument, which actually puts a nice table. So there were 163 calls, and I don't know how many numbers this is. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. As you can see, these are all the stuff that was called. Quite a bit for printing just one line of code. Not much, right? So the read, write, close, expected. The other stuff is actually related to runtime, like mmap and sig action, sig proc. We'll get to those. Clone, xxve is actually running the program itself, and some other stuff is actually mostly used by the Go runtime, right? So that's one. You can see all the details when you just do nothing. It gives you all you can see here. I'm going to show it here. This is a good line, right? This part. It actually calls write. Now you remember the first argument was a file descriptor. There's actually one, and then the string which I was printing. And in the end, what it equals to is 38 characters which were printed. Now, you can investigate the program, or any running program, or working anything like that anytime, because you can attach this to also running programs to investigate what's going on. So that's one example. There is a very useful way, especially for like if you're writing service and stuff, which a lot of people here do, I assume, right? How many people write service like backends? Hands up. So that's going to be useful for you. So I have a very stupid and very simple HTTP server here. Okay. Right? It doesn't do much. It basically takes the request and sends it back. That's it. Response. Right? Like whatever you ask it, it'll do. It will respond back. Now, what I can do is run this with a strace. And as you can see, it's kind of like waits on something. If you dig out and if you dig in the manual pages of Linux, you'll see what pwait means, but that's not really the cool thing. And if I try to curl it, it gives me something here, so it actually printed something. And then it's reading some, again, options, a lot of stuff. But maybe you're investigating a problem on the network. Cool thing you can do is put trace, trace, and what do you want on it? Well, you can do just a syscall, one exact syscall. So let's say read. Now it's going to write only read syscalls, nothing else, right? Pretty useful if you have suspicion that something's fishy. It's like something should be happening and it's not. Or you can also put some groups like network. And you see what stuff is happening on the program when it's running on the network side. Like this is useful when you're investigating connectivity issues, for example. Like, is it listening? Is it accepting? Now you see that all the ePOL stuff is out and so on. So I hope you're still here. Not bored yet. So if you need to debug stuff, this is your help. And the strace.io has a lot of examples. There's a ton of options what you can do. So that was pretty low level, right? And the good news is I'm not going to go further, right? Now I'm going to look at the different thing, and that's signals. How many people know what a signal is? Oh, yeah, cool. Using them, like really a lot. Time to time. I guess everybody's using it almost all the time. Just don't know. If you're pressing Control-C, you're just sending signals all the time, right? So, kill-9. I guess everybody did that. Or syscall if if you know the names. There's plenty of them, and you can look at them on pages. Signal, there's a whole page on this describing how it works in details. So, important ones: sigin, sigterm, and sigquit. I guess everybody heard about this, at least. I assume that you did, right? So, sigin, Control-C. Anybody pressing Control-C on the shell? I do it all the time. You see, you're using signals. Quite a bit. Sigterm, if you do kill and you don't give any argument, you're using sigterm. Or very often Control-C actually translates to sigterm somewhere else. And sigquit, which most people probably don't use, but that's when you need, if you want to do core dump. Anybody know what's a core dump? Okay, cool. So that's for another talk. Using core dumps in Go. But it basically is a dump to hold the memory of the process, and you can investigate afterwards what's going on. So, but how many people know SIG-UI Server 1 and 2? User ones. Way less hands now. Cool. That's very useful because those, they don't really have any meaning. You just get delivered and you can use them for whatever you want, which is very useful. Or I'm using those for example, increasing log verbosity. When debugging, I want to trace. You can just you issue the signal and you can switch. In runtime, you don't have to stop this program or reload config, something like that, right? Or handling the or anything else you come up with. It's like there's no limit on this. So, and I have prepared a couple of examples how to use this stuff. So now let's switch to another one. So very important one. The basic, I guess I have it here still. This is how you use it. You create a channel. There's just one. Don't forget to set the limit on the channel just for one, because otherwise you get like a ton of signals at the same time. And then you use package signal and, hey, package syscall again. Right? Doesn't work. It's actually not increasing. It's increasing size of everything, but not the code. Fun. Okay. But here, I'm saying I'm going to consume sig int and sig term, nothing else. Right? Actually, the sig int, sig term, and sig quit, and the user ones are the only ones which you can override and actually define like what they're going to do. The rest is actually given by the system, like the sig kill, for example. So very simple to use. You create a channel. You register that channel with what syscalls you want. And here, you just wait for it. Simple. Right? And I have a very simple application like that again. Basically the same, little more verbose. So you see what's going on. And now I'm waiting for a signal. The PID is there. I press Control C. Hey, it actually delivered interrupt, sig int. Now, let's say I want to do a different thing. I do kill, sig kill, sorry, sig term, and the bit is 37.068. Oh, I got program terminated. Cool, I handled the sig term now correctly. What if I'm wondering what happens if I do -9, right? If I kill it, like kill, like the real kill, not the funny stuff. So it's 27272, and it got killed. Like the program didn't handle it at all, I think. So that's the simple stuff. Now I have an example where it's useful, and that's very useful for servers, is to actually handle the sig term correctly, so you finish stuff gracefully. Right? Like graceful shutdowns. Very hard thing to do, because if you get, for example, if you're not doing it gracefully, maybe you're leaking some resources somewhere, and then you cannot connect to the database, or something worse. Right? So I have an example, which I think is going to be better to show here. Now, so let me see where I do have it. Big enough? Cool. It doesn't do much. There is some consumer. It's basically a simplified queue. I'm simulating some input here. There's going to be a producer that starts, and then there is a consumer that actually has some channels, like for the jobs and what to ingest the data coming in. And the important bit is the context. Everybody familiar with the context? Yeah, cool. Otherwise, this may be worth a talk, like how to use context correctly. And I start the consumer, and I'm using a work group here, right? Very useful. It spins up number of workers, 4, and here's the important bit. So now here, everything is running. Now the program starts, like the produce is producing. I have a wait group, I have consumers, they have workers, that's running. Now it's working fine. Now how to handle the sick term correctly in this case? Create the channel, the same thing. I actually handle a sick instance sick term, so if I Control-C it, it will happen too. And here it waits. I'm not even consuming the result because I don't care, right? And the shutdown is received, and I use the context to cancel everything, right, to stop. And wait for the workers to finish. And all is done. Very straightforward, I think. And basically, you should be using this every time you have something complex running, and you want to make sure that the stuff actually works. It's not, you're not leaking resources or keeping it like you have no idea what's going on if it's actually going to shut down ever, right? So I can just a quick demo. You see workers. Now a lot of work is happening. Blah 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 blah. I Control-C it, it takes time, but it finishes all the jobs and done, right? And it's using signal here. It's a sick term or second. So, and I'm gonna go a little up. Right, another cool feature is to use it for reloading stuff, like configs, if you don't want to stop and start over. Again, fairly straightforward program. I'm going to show it to you. It's config main go. Right. Again, some contacts because I need mutex now. I need to synchronize stuff. I don't want to override the config without, putting a lock around it. That's here. This function, actually, the read config function, what it does, it just reads the file and that's it. I'm actually using the file. I don't really, parse it in any way, but you could use YAML, for example, if you want, or whatever. And this is the interesting part, right? I have a swap config. I'm waiting for this user channel, and in the context, I read the config again. I lock it, read the config again. So it changes between the calls. And now the main function, boring stuff, again sets up the signal and runs the swap config function, the go routine. So it waits for the signal to come. And in the meantime, it will print whatever the config actually is. So it's clear how it works. And now you see it's going to print all value, all value, all value. If I go to, now I need to figure out where I am. So I have this here, the value. I'm going to rewrite it. Right. Still the old value, right? Like you can't even see now anything happening. It seems like nothing happens. Right? Like it's dead, but it's not. But I need that bit now. Sorry? Yes, exactly. I have to send the signal. It's the user one, right? US user. Now I have to look at what's the bit 38. Okay, I'm gonna copy it. It'll be better, right? So. And a new value, ooh, and still running, right? So this is another useful thing, how to do stuff without really stopping anything. And you can use sort of this trick. You can use to, for example, start gathering more metrics, or debugging outputs or whatever. All kinds of like this, all kinds of stuff. And that's it, right? For now.